Hello guys, how are you today? I hope everyone's doing well. So today for this video I'll be explaining the Chemistry AP chapter 1. I'll be doing the summary and the questions in the book. I don't know if this video is going to be long or short. Hopefully it's short so that I'll be able to post the chapter 2 and chapter 3 in time, as well as the math AMS. So why am I not doing any more of these shoutouts? Because unfortunately, a very sad and tragic incident happened last week. One of our previous physics teachers in my school personally had sadly passed away. So it's kind of out of respect and just for grievances that we're not gonna do anything that is anything like that for now. We're gonna keep these aside for later. I will continue them later on, but I'm just gonna leave this week as a week of grievances for our teacher. It's a very sad and tragic news. Hopefully his soul is resting in peace in heaven, inshallah. And I hope you guys also could pray for him, because it's a very tragic incident, and it's just all I wanted to say for now. So, the first thing I will be discussing in the summary notes is chapter 1. Okay, we start chapter 1 in AP Chemistry. The first thing we're going to be doing is talking about significant figures. Okay, so significant figures. I know it's a bit unstable, so let me try to more stable manner. Okay. My handwriting is not going to be the best because I'm writing on my tablet while it's upright, so it's going to be a bit difficult. So the first thing we're going to be discussing is significant figures. First of all, what is significant figures? Significant figures is something created by scientists, because usually, majority of the time, scientists get very, very large and huge, big values, which is hard to evaluate sometimes, and it's hard to keep track of what we need. So they created significant figures. Okay? They could say, for example, give me the 2 significant figures, 3 significant figures, etc. Now these, we will learn more about them, but first you will need to start with the base. The first thing that you need to know is always non-zero numbers are always significant. So non-zero numbers. So for numbers, I'm just going to write n like this. Non-zero numbers are always significant. Keep this in mind. Cannot write properly. Okay. Significant. So, insignificant figures, non-zero numbers are always significant. What are non-zero numbers? You have an example. 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are all non-zero numbers. That means whenever you see them, you will know that they are significant digits in a number. Okay? The second thing that you should know is that zeros between non-zero numbers are always significant. So, zeros between non-zero numbers are always significant. So, you can have, for example, numbers like 101, you can have 2,326, so not 2,000, 20,326, or you can have even 5,000, actually no, not 5,000, you can do 5,005, this is also a significant number. Why? So look, as you can see, the zeros, they are in between non-zero numbers. So when they are in between non-zero numbers, they are classified as as significant figures. Okay, very, very important. So zeros between non-zero numbers are always significant. Now, another very important thing is that zeros before non-zero numbers are never, pay attention, never significant. Okay, so let's take some example. You can take, for example, 0, 1, 0, 1. 0 is not significant. You only have one significant digit. Or, for example, 0.000000002. You have only one significant digit, because zeros that are before a significant figure, they are always not significant. You could have, for example, 0.5 0, 0, 0. So how many significant figures do you have here? This is a trick. You have 1, 2, 3, and 4 significant figures. Okay, because before the significant figure and before the decimal place, the zeros are not considered significant. Now, the second thing we move on to is zeros to the right of a number are significant only if there is a decimal place. So, zeros to the right of a number are only significant I said only. They are only significant if there is a decimal place. A decimal place. So, for example, like the example we took above, we have 0.500. Okay, here, as you can see before, there is a decimal place, but before, because they are before the significant number, then they are not significant. However, if it was 100.5000, this would be how many significant figures? This would be 1, 2, 3, 4, 5, 6, and 7 significant figures. Because look, you have 1, which is a significant figure, and then you have 2 zeros after it. So you know if they are after it, they are significant. But however, if you wrote 100, you will have how many significant figures? You will have only 1. Why? Because these 2 zeros, there is no decimal place after it. So like they said, as they said over here, zeros to the right, so you will take it to the right. Here it's 1, and you have 2 zeros to the right, are only significant if there is a decimal place. There is a decimal place, that means these are significant. There is no decimal place, that means that these are not significant. Okay, so that is it for significant figures. Now we will move on to discussing how to add and subtract decimals. So addition and subtraction. Addition and subtraction. So I will take as my example, I will take 100.5. One time we will do it plus 26.3. And then another let's do 356. Okay, so 100.5 plus 26.356. And another time we're going to do 100.5 minus 26.356. Now, how do you add and subtract these numbers? Very simply, what you're going to do is you're going to write them on top of each other. So you put the bigger number up always, 100.5. Plus, now here's the important part. You're going to put the decimal place with the decimal place. So for example, it's 26.356. So you'll put the decimal place over here. What comes after the decimal place? 3. What comes before the decimal place? 6. So now you just fill in the rest of the values. So it's going to be 100.5 plus 26.356. And then here you can just put zeros because these zeros don't really matter. Like, they are significant numbers, but they don't really matter. If you add them or not, it's going to be the same value. So, this is in addition. In subtraction, it's the same thing. So, it's going to be 100.5 minus, you're going to put the decimal place with the decimal place. What comes after the decimal place? 3. What comes before is 26. So, 3, 5, 6. Again, put the 2 significant zeros because, they're hidden zeros. You can still put them, and then you will just solve it and you will get your answer. So that is it for the addition and subtraction of decimal places. However, for multiplication, it is a different process. For multiplication and division, they are not the same as addition and subtraction. So multiplication is alone. Oh, and I forgot to mention over here, by the way, I forgot something very, very important. You will get your answer. Let us say you add them. You're going to get 6, 5, 8, 6, 2, 1. You will not keep it like this. Why? Because when you always take your answer, you have to take it to the smallest significant figures. What does this mean? You will look back at the 2 numbers and you will choose the one that has the smallest significant figures. This definitely for sure has the smallest significant figures, which is 4. So 1, 2, 3, 4. So here you're going to take 4 significant figures starting from the left. So it's going to be 1, 2, 3, and 4. You can round it if you want. It's better to round it. So if you were to round it, it would be 126.9. You will take it like this. So the same thing goes over here. If you were to subtract it, let's say you subtracted it, this will be 10. So you're left with 4. This will be 9. You're also left with 4. So 5 minus 3, that's 2. 10 minus 6, that's 4. 9 minus 2, that's 7. And then we have, oh no, my bad. Here I did a mistake. I forgot to take from the 5. So if you took from the 5, that's going to be 4. So 4 minus 3, that is 1. Okay, here you take from the 1, it will be 0. So it is 74.144. Alright, so that's my mistake over here. So again, you're going to take it to the smallest significant figures. You will look back. It is 4. Okay, so you're going to take it 1, 2, 3, 4 significant figures. If that's the case, then the answer is going to be approximately 74.1. Why did I do it like this? My bad. 74.14. You're going to round it to the smallest significant figures. Now we move on to multiplication. Let's take again our same example, which is 100.5. This time it is multiplied by what? It is multiplied by 26.356. Okay, so let's say this is the case. If this is the case, you're just going to do regular multiplication. So 26.356 times 100.5. It doesn't really matter. You can just multiply it regularly. Multiply it like normal numbers. I'm just going to use my calculator for this to be a bit faster. 0.356. So here you will get an answer which is what? 264. Let's just say you multiplied them regularly. 2648778. So actually 7780. So how do I know where I should put my decimal place? Very simply. Does not take anything. You just need to count how many digits are after the decimal place combined. So after here, you have how many? You have 3 digits after the decimal place. Here you have 1. So 1 plus 3, that's gonna be 4. That means in your final answer, you have to put it after the 4th decimal place. Okay, so you're gonna count 1. Actually, no, it works from this side. You're gonna count 1, 2, 3, and 4. And then you are going to put it over here. So your answer is going to be 2648.778. However, for division, let me take an easier number for the division. So let's say you're going to do 11 divided by what? Divided by 5.50. Let's just say you're doing 11 divided by 5.50. Okay, so what you're going to do in this case is you're going to take the bigger number 11 and you're going to put it under these stairs. And then you're going to take this number over here, which is 5.5. Now, usually this number over here, what happens to it? It can never be decimal. So this number over here can never be a decimal place. In order to make this work, you're going to multiply by 10 over here and you're going to multiply by 10 over here. It's the same thing as a fraction. So it's 11 over 5.5. You cannot have a decimal in the fraction. So you're going to multiply up and down by the same number, which is 10. If you did that, you're going to get 110 over what? Over 55. So then you can divide. It will become 110 divided by 55. You will get the same exact answer as here if you put it on your calculator. And you're going to get an answer of 2. But how will we put it? We know we will look back to our answer. You will see how many significant figures does the smallest one. So remember, it's always the smallest significant figure you will take. Same for this one over here. I forgot to mention. So you will take the smallest significant figure. This has 3 significant figures. This has 2 significant figures. So for sure, I will take it to 2 significant figures, which is 2.0. And that's my answer, 2.0. For here, you'll choose the smallest. In this case, it's going to be 4. So you're going to count 1, 2, 3, 4. In this case, you're going to round it. It will be 2649. Very simply. Okay, so that is it for the multiplication and division. Now we move on to some definitions. Very simple definitions. First thing is accuracy. What is accuracy? Accuracy is what? It is the agreement of a particular value with the true value. So very simply, accuracy, you want to see how accurate your number is. You will see how much does it agree with the true value of this number. For example, a very famous example is you're gonna see, for example, pi accurate to 2 decimal places is 3.14. Whereas in real life, pi it is what? Pi it is 3.141592654, etc. So if you were to round it, it is accurate to how much? to 3.14 compared to the actual value, which is 3.1415 whatever. It is relatively accurate. This is the definition of accuracy. The next thing that comes across is what is precision. So precision refers to what? It refers to the degree of agreement among several measurements of the same quantity. So, for example, you want to check, you did an experiment and you want to check how accurate, how precise your experiment is. In order to do that, you're going to repeat your experiment many times, okay? And you're going to take the same measurement. If it's the same among all of the times, then definitely for sure your experiment is precise. After precision, we have what? We have random error. This is very important. Random error, it is what? Indeterminate. So you don't know from where it is. Okay, it's just like any random. Or indeterminate, you cannot determine it. What does a random error mean? A random error means that a measurement has equal, sorry for the pause, equal, I'm just copying, probability of being high. I forgot how to write high, oh my goodness. Okay. Of being high or low. Honestly, how I would remember this is random, random probability. So if it's random, then definitely you have a probability. Now the final thing we will discuss is what is systematic error. Systematic error. What about systematic error? It is determinate, meaning it can be determined. What happens? It occurs in the same direction each time. Each time. This means that it is either very high. So if it's occurring in the same direction each time, let's say for example, you have an error of +2. This is a systematic error. Let's say you're weighing something and the systematic error is coming from the scale, let's say the balance, okay? Or the scale, the electronic scale, and it's adding by itself, let's say just 2 grams. So if you're gonna weigh anything, there's gonna be an addition of 2 grams. So it's happening in the same direction each time. So it's either very high, it's either always very high, it's either very high or very low, always. There's no intermediate and there's no being both at the same time. Okay? Now the last thing I will discuss before moving on is something called exact numbers. So I'm going to do part 1, part 2, part 3, each one for a different chapter. So exact numbers, although for part 3 I don't think there will be a summary because it's literally just straight to the point solving. So exact numbers, they are what? They are numbers that are not obtained by measuring. So they are numbers that are not obtained by measuring. Okay, they are not obtained by measuring devices, okay, but by counting. So for example, let's say I have 5 water bottles. How do I know it's an exact number? I have exactly 5 water bottles because I counted 1, 2, 3, 4, 5. Okay, but by counting. Okay, in formulae, so in a formula, for example, just take the example of the circumference of a circle, which is 2 pi r. You know that this is always the circumference of a circle, so it's always exact. Okay, and then in definitions. So in definitions, so for example, you have like a dozen means 12, or you have a quarter of something. Quarter means what? Quarter means 1/4, etc. Just these defined values. So this is kind of the summary for chapter 1 AP Chemistry. Now I'm gonna move on to the CQDs to solve them. Okay, so my tablet did a new update. Please ignore the thing on the top. I got confused a lot because of it, so please don't get confused like how I am confused. So anyways, let us move on to the first question. So they said, give the number of significant figures in each of the following values. The first value we have is what? Is 600 milliliters. As you can see over here, there is a decimal place. So zeros to the right of a number are only significant if there is a decimal place. That means these zeros, they are to the right of 6. They are significant because there is a decimal place. So that means there is 3 significant figures. Whereas over here, since there's no decimal place, it's only going to be 1 significant figure. This value over here, it's a bit tricky. So you will never ever look at the 10. Do not ever look at the 10. Only focus on the value itself. How many significant figures does it have? It has 7. And then after the decimal place, it has 1 0. So that means it has 2 significant figures. This over here, you will remember that any numbers before significant figures are not vital, and you have to make sure that the zeros are either followed by a decimal place or they are after the decimal place in order for them to be significant. So in this case, it's going to be 1, 2, 3, and 4, and 5 significant figures. Okay. This is a trick. Okay, very, very important trick. 28 students. Now, actually, something I forgot to mention in the previous one is that when it is an exact number, okay, it will have infinite significant figures. So, because it has an exact number, because it's an exact number of students, can you have half a student? What will you have? Like the body of the student and his legs are left behind? Or like his legs come and his body doesn't come? No, that does not make sense. For example, a bottle, you can have like half a bottle because you can drink the water inside the bottle. But this we're discussing with what? We're discussing with the liters of water, whereas in reality, can you have half a bottle? Can you take a plastic bottle, cut it in half and say, look, I have 4 bottles and a half? That does not make sense logically. So if it can be an exact number, then what? Then you say that it has infinite significant figures. This one over here, it's not an exact number, so you will just count. It has 1, 2, and 3 because these are not followed by decimal place, so it has only 3 significant figures. I'm gonna go back over here and I'm gonna say that exact numbers have infinite significant figures. Okay? So let me go back. How do I do this? Here and here. There we go. Okay. So, that is it for CQD number 3. We move on to this one over here, very important. Calculate the density of the liquid. I remember this came in the AMS. So, you should remember the equation that density is equal to mass over volume. So, how do you find the volume of the liquid? Because we're calculating what? The density of the liquid. Actually, the volume of the liquid is given to us. It's 20.0. So in this case, you have to keep this in mind. 20.0. This is the volume. However, how do we find the mass of the liquid? This is going to be a bit difficult. Why? Because you cannot measure mass of liquid by itself. What you should do instead is measure the mass of the mass of an empty flask, okay, and then add liquid to it, and then you will measure the mass of the flask plus liquid. So in this case, in order to find the mass of the liquid, you're going to subtract the mass of flask plus liquid plus minus the mass of the empty flask. So it's 42.6. Thank God you can use a calculator. It's going to be much easier. 42.6 minus 18.99. That's going to be what? That's going to be 23.61. So the mass is 23.61. I'm just going to assume grams because in chemistry we're always using grams. So the density is equal to 23.61 over what? Over the volume, which is 20.0. And you're going to get an answer which is 1.1805. Now pay attention to these significant figures. Take the lowest significant figures. In this case, it's going to be 3. So you're going to count 1, 2, 3. You cannot round it. So to 3 significant figures, it is 118 gram per centimeter cubed. I'm just going to assume this is what they want, even though they did not give us any units. Because usually this is the unit for volume in chemistry. Okay, so we finished this exercise. We'll move on to the next one, which is CQD number 4. So they said, complete the following table. Okay, you have mass of the empty flask to be what? To be 121.01 grams. And then mass of the flask filled with water, it's 321.01 grams. So in order to find the mass of water, you're going to subtract them. So 321.01 minus 121.01. The difference is going to be the mass of water, which is 200.00, keep these in mind, grams. And then you have the density of water, which is 1 gram per centimeter cubed. Now, very important, they want us to find the volume of water. You know that density is equal to mass over volume. That means volume is equal to mass over density. You have the mass in grams, which is 200. Make sure they're the same unit here and here. So 200 grams divided by 1 gram per centimeter cubed. You're going to get what? You're going to get 200 centimeter cubed. But if you change its units, it's going to be what? It's going to be 200 milliliter. So very simply, it's going to be 200 milliliters over here. Also, excuse my breathing. I have some breathing issues. So I'll have like some weird breaths every now and then. Okay, if you ever get annoyed of my breathing issues, please ignore them, okay? Mass of the flask filled up with CO2 gas. Okay, mass of the CO2 in the flask, number of moles of CO2, temperature, and pressure of CO2. So now they said that they removed the water from the flask, okay? And instead of water, they put CO2. So instead of 121, it now became 123.2. So how much is the mass of CO2? It's becoming 2.2 grams, because you're going to subtract 123.2 minus 121.01. You will get 2.2 grams. So the mass of CO2 it's 2.2 grams. Now, the number of moles of CO2, how do we find the number of moles of CO2? Very simply, number of moles is equal to the mass over the molar mass. So it's 2.2 grams over the molar mass of CO2. How do you find the molar mass of CO2? You look in the periodic table. Carbon has a molar mass of 12 plus oxygen, which is 16. How many oxygens do you have? You have 2, so 16 times 2. So 12 plus 16 times 2, you're going to get an answer of 44. So it's going to be 2.2 over the molar mass, which is 44. You will get an answer of 0.05. So it is 0.05, but pay attention. This is one significant figure. We need it to 2 significant figures. So in order for us to make it to 2 significant figures, we're going to add a 0 over here. So 0.050 moles. Very important. Now you have what? You have the number of moles, you have the temperature, you have the volume of the flask, which we found up to be how much? To be 200 milliliter. They want us to find the pressure of CO2. So look, we have pressure we need to find, we have the temperature, we have the number of moles, and we have the volume of the flask. And you should remember that the ratio R is equal to what? It's equal to 0.082. So in this case, we can apply the equation PV equals nRT. So in this case, the pressure is what we need to find. So pressure times the volume, which we found up to be 200 milliliters, is equal to the number of moles, which is 0.050 moles, multiplied by R, which is 0.082, multiplied by what? By the by the temperature, which is in Kelvin. Always remember it should be in Kelvin, so 300 Kelvin. Okay, now to find the pressure, you're just gonna change the equation, so it becomes pressure is equal to 0.050 times 0.082 times 300 over 200 milliliters. So put them on top of each other. Times 300 over 200 milliliters, you're gonna get an answer which, if you round it to the correct number of significant figures, which you can see very clearly, it is what? You will take the least significant figure. So this is 2, this is 2. So definitely you will take it as 2 since the least significant figures is 2. So I got 6.15, okay? Oh, but I did a mistake, a very, very big mistake. I did not change the units. So we found what? We found the volume of the flask in milliliters, but I forgot to change it into the SI unit, which is what? Which is liters. In order for me to change it to liters, it will be 200 milliliter times 10 to the power of minus 3. So it's 200 times 10 to the power of minus 3 liters. Very, very, very important. So now my whole answer will be wrong because what? I forgot to change it to its SI unit. Please pay attention to this. So I got what? I got that P is equal to 6.15. I will round it to two significant figures for it to become 6.2. So that is it for CQD number 4. We move on to the top question, which is CQD number 5. Okay, in a laboratory session, grade 12 students were given an unknown gaseous substance and asked to find its molar mass. To do so, one group of students obtained a hard flask and did the following. Firmly closed the flask and measured its volume, V equals 1000 milliliters, filled the flask with dry air, firmly closed it and measured its mass, 100, okay, whatever. Then measured the temperature of both gases, measured the pressure, and found the density of dry air. They want us what? To find the mass of the dry air. We know that the equation what? The equation is that density is equal to mass over volume. So mass, what we're looking for, is equal to volume times density. Where is our volume? Our volume, we know that it is, this is volume. Our volume, we know that it is 1000 milliliters. You need to change it into its SI unit, which is liters. So it is 1 liter. 1 liter. Quite simply, 1 liter. Multiplied by its density. Where do you find its density? You find it over here. Very simply, 1.19. So you put it on your calculator. No need actually, it's very easy to do it mentally. You're gonna get 1.19. Now, check the small significant figures. This one has 3 significant figures. That means our answer is gonna have 3 significant figures. Just like that, we found the mass of dry air in the closed flask. Now, find the mass of the completely empty closed flask. Okay, so the mass of the completely empty closed flask is gonna be what? They told us they filled the flask with dry air, firmly closed it, and its mass became 157.7 grams. So the mass of the completely empty closed flask is gonna be 157.70 grams minus 1.19. So it's gonna be what? It's gonna be 156.51 grams. Of course, round it. What's the significant figures? This is 1, 2, 3, 4, 5. This is 1, 2, 3. So you'll round it to 3 significant figures, which is almost 157 grams. That is it for part B. We move on to part C. Find the mass of the unknown gas in the closed flask. They told us then, after that, they filled the flask with the unknown gas, firmly closed it, and measured its mass. So we know what? We know that the mass of the unknown gas, it's going to be the total mass that they found over there, which is what? Which is 158.08 grams. 158.08 grams. They will subtract it from the answer we got in part B, which is the mass of the completely empty closed flask, which is 156.51 if I'm not mistaken. Subtract them, you will get an answer which is 1.57 grams. Alright, so this is 1.57 grams. Now they said find the molar mass of the unknown gas. Okay, so let's go back up and see what is given after that. So we have the molar mass, we have the mass of the gas, and we need to find the molar mass. We also have the temperature of the gas in degrees Celsius. We have the pressure of the gas in degrees Celsius. And so technically that is all that we need, because our equation that we will be using, it is what? It is PV is equal to nRT. Very simply. The pressure, we have it. We have that the pressure was 850 millimeters of mercury, if I'm not mistaken. Whenever they give us 850 millimeters of mercury, remember, we will not accept millimeters of mercury. We need to change it directly into atmosphere. So in order for us to change it into atmosphere, we will need to divide by 760. So if I'm not mistaken, it was 850. So it's going to be 850 over 760 times the volume. If you remember the volume, we found it to be 1 liter. Okay, so times 1 liter is equal to the number of moles, which is mass over molar mass. Okay, multiplied. So actually change the mass. We know what the mass is. We need to find the molar mass. The mass, it is actually 1.57 as we found it in part B, multiplied by the constant R, which is 0.082. Okay, and then all of it multiplied by the temperature. We have the temperature, which is 25 degrees Celsius, but plus 273 because we need it in Kelvin. Now, after moving the m over here and moving this over here, our equation is going to look something like this. It's going to look like the molar mass is equal to what? It is equal to the mass, which is 1.57, times r, which is 0.082, times 25 degrees plus 273 over what? Over 850 over 760, because we needed in atmospheres. Okay, times 1. So you put it on your calculator. Let me put it. 73 over 860 over 760. 850. And you are supposed to get an answer which is 34.3 grams. Of course, you will take it to the smallest significant figures. In this case, I think this was 1, so 0.0821. So that means the smallest significant figures would be 3 significant figures, which is 3.43. And just like that, we finished the... Oh, actually, sorry, you find the mass in part C, not in part B. So we finished calculating the molar mass of the unknown gas. So we move on to part E. They said when all the students finished their calculations, the teacher announced that the unknown gas is hydrogen chloride, HCl, which has a molar mass of 36.5. Find the percent error in the experimentally determined molar mass. So to check the experimental error, what you're going to do is you're going to do the actual minus what we got. So actual minus gotten over actual times 100. So in this case, it's going to be 36.5 minus 34.3 over 36.5 times 100. Put it on calculator. And you will get an answer of what? You will get an answer of 6.03. So the percent error is what? 6.03%. Keep this in mind. Now, two possible scenarios were suggested by the teacher to explain the variation between the experimentally determined and the actual molar mass. The teacher asked the class to check if each of the two scenarios alone can cause the variation noted and justify their answers without any numerical calculations. First scenario, the HCl did not replace all the dry air and therefore some dry air was still in the flask. So the first scenario, the HCl did not replace all of the dry air and therefore some dry air was still in the flask. This means what? This means that this explains the variation in mass. It explains the difference in mass. The difference in mass. Why does it explain the difference in mass? Because the molar mass of dry air is less than the molar mass of HCl. So when you're measuring the mass of HCl in the flask, it will be less than it's supposed to be because the entire sample is not pure HCl. Okay? So the calculated molar mass will be less than the actual mass, which is then which is the actual mass of HCl. So the second scenario, the temperature of the dry air is 25 degrees, but the temperature of HCl was actually less than 25 degrees. Okay, look, the temperature has nothing to do with the difference in mass of gases. However, listen, if the temperature will not have anything to do with the difference in mass of gases. So it does not, here we can say, doesn't explain difference in mass by variation. Okay? Sorry for the bad handwriting, by the way. So what actually happens is that as the temperature decreases, the density is gonna increase. So with a constant volume and an increase in density, so you know the equation is mass is equal to density times volume. The volume is constant, but the density is increasing. That means for sure the mass is gonna increase, which will make it more than the actual mass, which is not the scenario. So we move on to 6th top. Is 6th top the last question? Yeah, I think 6th top is the last question, and then I'll stop the video over here. So one of the important skills grade 12 students must master is gravimetric analysis. Okay? Experiment 1. Students were given hydrate of copper. Okay, and we're asked to find the N. Okay, they want to find the number of moles of water. To do so, the students followed the following steps. They weighed an empty crucible. Okay. They added sample and waited, or it's not waited, they weighed the crucible again. They heated the crucible for 5 minutes, let it cool, weighed it, etc. They heated the crucible for further 5 minutes, let it cool, etc. They heated the crucible for further 5, okay, whatever. So they started their calculation. They told us, given that the molar mass of CuSO4 is 159.61 and the molar mass of H2O is 18 grams per mole, they said, why did the students heat the crucible only 3 times? Well, if you look at it properly, you will see that between the second and third time that they heat it, there is literally barely any change in mass. So the answer you're gonna say over here is that there was barely any change in mass, okay? And because there was barely any change in mass, you can say what you can say, that it leads to the conclusion, or we can conclude, so we can then conclude that all the water had evaporated. All water had evaporated. Okay? So very simply, that is it. Now, deduce the formula of the hydrated copper sulfate. Okay, very simply how I would like to do this is, I would like to take into consideration, I'm getting messages on my phone, please ignore that. I would like to take into consideration how they plotted it. They said 1 CuSO4, so we're going to keep this in mind. Whatever value we get, we need to change it. We need to be able to change it into 1. So deduce the formula of the hydrated copper 2 sulfate. In order to do that, we will need to find, first of all, the mass of water and the mass of copper sulfate. So as you can see over here, this is what? This is the final mass of what? Of the anhydrous, or the without water copper sulfate. So CuSO4. Okay? But it's the final mass of the copper sulfate in what? In the what? The crucible. So look over here. Over here you have the mass of the crucible plus the sample is 48.281 grams. Whereas the mass of the crucible itself is 47.599 grams. So the actual final mass of the CuSO4, so mass of CuSO4, it's gonna be the mass of crucible plus sample, which is 48.281 minus 0.281, I don't know what I did over here, minus 47.599. You put it on your calculator, you solve it, you're going to get an answer of 0.682 grams. So this is what the mass of, the final mass of CuSO4. So in order to get the number of moles N of CuSO4, very simply what we're going to do is we're going to take the mass, 0.682, divided by the molar mass, which is 159.61, and we will get like an approximate answer to be 4.27 times 10 to the power of minus 3. So now we have what? We have the number of moles of CuSO4. So I'm just going to erase all of this. We have N CuSO4. It is what? It is 4.27 times 10 to the power of minus 3 moles. Now the mass of water. Okay, in order to get the mass of water, what we're going to do is we're going to take the biggest mass of the crucible plus sample, which is 48.659, and we're going to subtract it from the smallest mass, which is 48.280. So 48.659 minus 48.280, put it on your calculator, you'll get an answer of 0.379 grams. To find the number of moles of H2O, so you have the mass of water. We want to find the number of moles of water. It's going to be mass over molar mass. So 0.379 over 18, you will get it to be 0.0210 moles. So the number of moles of H2O is what? It is 0.0210 mole. Now, in order for the CuSO4 to become what? We want it to be 1 mole of CuSO4. We'll need to divide it by 4.27 times 10 to the power of minus 3. Meaning, in order to get this to N moles, we'll also need to divide it by 4.27 times 10 to the power of minus 3. So, 0.0210 over 4.27 times 10 to the power of minus 3 it will give us an answer which is approximately 4.9. We cannot put any values that are not an integer, so it needs to be a whole number. So you'll round it to 5. That means n is equal to 5. Very simply. We move on to part C. In part C, it says, in some groups, heating the solid led to some of the solid splattered out. How will this affect the calculated mass of the evaporated water? Justify your answer. So, if some of the solid was splattered out, they will consider that this change in mass is what? It is the evaporation. They will think that this is the result of the evaporation of water. So, as a result, the calculated mass that is splattered out will be added onto the calculated mass of the water, okay? So actually the calculated mass of the evaporated water will be greater than the actual mass. That's why they need to be very, very, they should be dealing with it delicately. Students were given a mixture of anhydrous CuSO4 and KNO3 and given the task of calculating the percentage of CuSO4 by mass in the mixture. To do so, the students followed the following steps. They weighed the given mixture, M mixture equals 5.42 grams, dissolved the mixture in water to form an aqueous solution, added excess BaNO3 to aqueous to formed solution, found the mass of BaSO4 given this. Okay, list the steps needed to find the mass of BaSO4 precipitate form. So, the steps needed to find the mass of BaSO4 precipitate form is what? You have, first step is to filter the precipitate. PPT means precipitate, so you will filter the precipitate. The second step is what you're going to do. You're going to wash the collected residue with distilled water. Okay, sorry for the bad handwriting. While you wash it with distilled water, you wash it with distilled water to make sure that there is no more impurities, okay? Or to clean it, okay? And then after you wash it with the distilled water, you will leave it to dry completely. And then the third and final step, what you're going to do is you're going to calculate the mass of the residue by difference. So you're going to do, my bad. So, the difference in mass from the initial to the final is what? It's going to be the mass of the residue. So, calculate mass by difference. Okay, very simply, these are the three steps. We move on to part E. The mass of BaSO4 precipitate was measured to be 5.5 grams. Calculate the percent of CuSO4 by mass in the original mixture. Okay, so this will not require a lot of thinking. You just need to take CuSO4, okay, and BaNO3 2. You split them into their ions. What are their ions? Cu2 plus, SO4 2 minus, Ba2 plus, and what? And SO4, no, not SO4, sorry, NO3 minus. So Ba2 plus and NO3 minus. So as you can see over here, they will switch with each other. So you will get CuNO3 2 and BaSO4. But as you can see over here, there's actually no need for the bracket. You can just write BaSO4. But as you can see over here, CuSO4, BaSO4 is going to have what? The same number of moles because there's no change. Nothing was gained here and nothing was lost here. So CuSO4 is going to be the same number of moles as BaSO4. So the mass of the precipitate BaSO4, which is 5.5 grams, divided by the molar mass, which is 233, just put it on your calculator, you will get 0.0236 moles. You will know that this is also the moles of what? Of CuSO4 as well as BaSO4. Why? Because previously in the mixture, it's going to have the same mass as finally in the mixture. So now what we're going to do is we're going to find the number of moles of CuSO4. N of CuSO4, it's gonna be what? It's gonna be the not the number of moles, the mass. The mass of CuSO4. So M of CuSO4 is gonna be what? It's gonna be the number of moles times the molar mass. What is the number of moles? It is 0.0236 times the molar mass. You should know how to find it. It's gonna be 159.6. You put it on your calculator, you will get approximately 3.77 grams according to the correct number of significant figures. Now here's where the percentage part comes in. You will take the mass of CuSO4, which is 3.77, over the total mass of the initial, which is 5.42, multiplied by 100. So if you put it on your calculator, 3.77 over 5.42 times 100, you will get an answer which is approximately 6.55. So you will round it to 3 significant figures. Not 6.55, sorry, 69.55. So you will round it to 3 significant figures. It will be 69.6%. So just like that, we finished the first chapter. We will leave the second chapter for the next video.